Here's the picture so far. We have a primal program over here trying to be maximized, and we have a dual program over here trying to be minimized, and the obvious question is, do they ever meet? Well, the answer is yes, they always do. More precisely, we state this as follows in the duality theorem. If either the primal problem or the dual has a finite optimal solution, then so does the other, and the optimal objective values are equal. And if either problem has an unbounded objective value, then the other is infeasible. Note that it is possible for both the primal and the dual to be infeasible. We'll start the proof by showing the second part. If either problem has an unbounded objective value, then the other has no feasible solution. So we'll suppose that the primal is unbounded and that y is feasible for the dual. Well, by weak duality, B transpose y must be at least ct times x for all feasible x, but since the primal is bounded, there has to be an x that's larger, and that creates a contradiction. The case where the dual instead of the primal is unbounded is analogous. Now we turn to the first part of the proof, and we want to show that if either the primal or the dual has a finite optimal solution, then so does the other, and even more, that the optimum values are equal. Let's start with the primal having a finite optimal solution. Well, that then implies that it has a finite optimal basic solution by the fundamental theorem of linear programming. Let's let the basis be the first m columns of the matrix A, and we'll divide up x and c in the usual way. Remember that B stands for basic here. Recall then from the simplex algorithm that this vector RD, which represented the effects of moving along one of the directions in xd, had to be non-positive. Otherwise, this basic solution wasn't optimal. Now we're actually going to construct a solution for the dual. We'll let y transpose be cb transpose times b inverse. And then from the non-positivity of R, it follows that y transpose d has to be at least as great as cd transpose. And then we can show feasibility by arguing that y transpose A, and we can just rewrite that in terms of the submatrices B and D. Well, just by definition, the first part is just CB transpose, and the second part is this expression here, which again from the fact that RD is non-positive is at most CB times T. Well, that's just our vector C, and we can see that y does in fact meet the feasibility constraints. Moreover, y transpose b, that is the objective function for the dual program, is equal to cb transpose times b inverse times b. But b inverse b, that's equal to xb. And c transpose b times xb was the value of the objective function for the primal. So these are equal, and then by weak duality, it follows that our choice of y is optimal.